In a parallel circuit, we have more than one path for current to follow. So I'm going to draw this one, and I'm going to put a line there, and I'm going to put another line here. And I'm using these different colors because in any given wire, the potential is the same. So right here, if this is 48 volts leaving that battery, after R1 happens, well, there's 2 amps of current. 2 times R is 40. That's 40 volts of energy that's gone. That only leaves me 8 volts of potential in this one. And now we're back to 0 because we're on the 0 side of that battery, right? And so we can see the 40 volts of potential difference comes through, and then we got 8 volts of potential difference right here, and then 0 volts, and so the 48 in and the 48 out are the same. Well, when we have a parallel circuit, let's again make this a 48 volt battery. The top of this is at plus 48 volts. The bottom is at 0 volts, and that's true along this whole wire. Wires are perfect conductors. They don't consume any energy. And so I'm going to go ahead and put in a couple resistors. I'm going to put in R1, and I'm going to go ahead and let R1, just like before, have a 20 ohm resistance. And I'm going to put in R2, and we'll go ahead and let R2 have, actually I'm going to make it a 5 ohm resistance. Now, what do we get when we see what's going on here? Well, if you think about what I did, when I added R2 in parallel, multiple paths, now I said current can come this way or current can go that way. I added that resistance there, and that actually opened a path. And because it opened a path, it actually allowed more current to flow. So here, adding resistors open paths and allows more current. So parallel, multiple paths, and what we see is adding resistors allows more current. Because it adds more paths. Over here, adding a resistor, we were putting an obstacle in the way of current. Over here, when we add a resistor, we are putting an opening for more current to flow. It couldn't flow here before, now it can. But because they're connected across the same 2 wires, they have the same voltage, right? So the potential difference from here to here and the potential difference from there to there are the same. So there's a lot of math here that we could do. But essentially, right, if I want to know how much current is coming out of that battery, then I need to apply Ohm's law again. V equals IR. The voltage coming out of the battery is 48. Well, that's the same as the voltage across here. The current leaving this, the total I, I'm going to call it IT, splits, and I get I1, some of it comes this way, and I get I2, some of it goes that way. Now it comes back around, and I've got I2, and this one comes back around, and it's I1, but then they come back up in their I, because again, we can't create or destroy charge. And so what we see is the total current is V equals I total times R total. The total current leaving the battery is equal to the total resistance. Well, how are we going to get that? Well, over here, that voltage is the same because it's across the same 2 points. That's also equal to I1 R1, which is also equal to I2 R2. Okay, so what I have is all of these are equal to each other. IT RT is the same as the voltage, which is the same as I1 R1, which is the same as I2 R2. Now, I'm going to go ahead and apply the law that says charge is conserved. So IT is equal to, that's an I, the current, the total current is equal to I1 plus I2. Now, because all of these are equal to V, let's go ahead and solve these, right? So I have the total current, IT, is equal to V over RT. So I have V over RT is equal to, and then I1 would be V over R1, V, whoops, this isn't V1, all the volts are the same, over R1 plus V over R2, that's current. And voltage is everywhere the same, so can cross those out, and I have 1 over RT, the total resistance, equals 1 over R1 plus 1 over 2. Now, this is really weird because that's not total resistance, it's the reciprocal of total resistance. So let's see how we deal with that. Okay, so if I want the total resistance of this circuit, what I can say is 1 over the total resistance is equal to 1 over 20 plus 1 over 5, because those are the individual resistances of the resistors. And remember, to add fractions, we need a common denominator. I'm going to multiply both sides by 4, top and bottom, not both sides, both top and bottom by 4, which gets me 1 over 20 plus 4 over 20, which is 5 over 20. But this is not total resistance, this is 1 over total resistance, so I'm just going to flip both sides over, so I actually get total resistance. Total resistance is 20 over 5, which equals 4 ohms. Now, that's kind of neat, because what that tells me is the total resistance of this whole circuit is less than any of the individual resistances. And that's because there's multiple paths. So not all of the current has to go here. Not all of the current has to go here. And so the total resistance is less than the smallest resistance. Adding resistors allows more current. Now, what is true in parallel circuits is this assumption right here: the voltage is everywhere the same. So that's a good one to know. Voltage is everywhere the same. Okay? So that's different than what we had in a series circuit. In a series circuit, we had current is everywhere the same. In a parallel circuit, we have voltage is everywhere the same. And since now we know the total equivalent resistance is 4 ohms, we can also figure out how much current is leaving the battery. Because V equals IR, we have total voltage of 48, we have a total resistance of 4 ohms, so I divide both sides by 4 is equal to 12 amps. We have 12 amps of current. Now, all of those 12 amps don't go through each one of those. Instead, we could say, well, this resistor is 20 ohms, and it's got 48 volts of potential difference, so we would say V equals IR, and we would have 48 equals I1, and this is R1, which is 20, and we would divide both sides by 20, and we would see 2.4 amps. And then we could do the same thing over here, and we would get 48 V equals I times 5, and 5 goes into 48 9.6 times, and 9.6 plus 2.4 is the 12 amps that we said we should get. So energy is still conserved, it's just different in a parallel circuit than in a series circuit.